All right. In this video, I'm going to go over how to do the circular motion worksheet. So here we go. So these first couple questions it's all broken up, which is sometimes confusing. And the idea here is just to kind of make a couple different points, which I'll make as I go along here. So we have this 1.5 kilogram rock is whirled around in a flat circle at the end of a 85 centimeter long string. Let's keep in mind that we would want to change that to 0.85 meters. It has a linear speed of 1.8 meters per second. Name the force that is causing the acceleration. So the force that's causing the centripetal acceleration is tension. What is the magnitude of the centripetal acceleration? So let's just remember that centripetal acceleration is just v squared over r. So that would be 1.8 squared divided by 0.85, and that's going to give you 3.81 meters per second squared. What is the magnitude of the centripetal force acting on the rock? You could just do F is equal to ma for that. So that's just going to be m, right? 1.5 kilograms times by 3.81 meters per second squared, and that's going to give you 5.72 newtons. So what is the magnitude of the tension on the string? So, right, I mean, we just, in part A, we said that tension is what's causing the centripetal force. So, um, right, it's also 5.72 newtons. Okay, moving along. A 1,400 kilogram car drives around a corner with a radius of 45 meters. If the coefficient of static friction between the tires and the road is 0.82, what is the maximum force of friction? Word maximum is just because, right, keep in mind that the force of friction is usually less than or equal to mu. So the maximum would be when FF is equal to mu normal force. So it would just be 0.82 times by the weight of the car, which would just be 1,400 times by 9.8 or 10, and that's going to be 11,000. So that's your 11,250 newtons. What is the greatest speed the car can have in the corner without skidding? So for that, right, then we just have, right, we look toward sum the forces towards the center of the circle. So sum your forces towards the center. It's going to be ma is equal to force friction. So that's going to be m v squared over r is equal to force friction. We're solving for v, so v is equal to ff times by r divided by m square root r 45 divided by m 100 So there you go. V is equal to, I believe, 19 meters per second. All right, next up, driving in your car with a constant speed of 12 meters per second, you encounter a bump in the road that has a circular cross section. What two forces are acting on the car at top of the bump? So let's assume that we're not going so fast that it's airborne. So we would have the force of gravity, and we would have the normal force. So those would be your two forces. Okay. If the radius of curvature of the bump is 35 centimeters, find the normal force of a 67 kilogram person in the car as you pass over the bump by summing the forces you identified in part A. So, by the way, right, force of gravity needs to be bigger because we need a net force towards the center of the circle than the normal force. It's also why you feel slightly lighter. So we sum our forces towards the center of the circle. That gives us m, and then the a is, of course, going to be v squared over r is equal to, right, force of gravity minus normal force. We're solving for the normal force. So normal force is going to equal, I'm going to go ahead and change force of gravity to mg minus mv squared over r. So then m is just going to be, right, we got our m is 67 times by g, which is 9.8. Realize I'm using 9.8 instead of 10. You can just change it if you need it. Let's see here. R is, what was it? 35. No, what? Oh, shoot. That's not where that goes. Sorry. I was getting all distracted by my 10 here. Here we go. 67 times by 12 meters per second squared over a 35. There we go. If you calculate that all out, you get that normal force is equal to 656.6 minus 275.7. So your normal force is equal to 381 newtons. So, all right. Just a couple of points on this, right? So remember that your normal force is going to, right, towards the center is positive. So that's the reason it's force of gravity minus normal force. And then the force of gravity needs to be bigger than the normal force because you need a net force towards the center of the circle. So, all right. Next one here. A hockey puck with mass of 0.17 is attached to the table, passes through the hole. The hockey puck moves in a circular radius of 0.5, tied to the other end of the string and hanging vertically beneath the table is a 1 kilogram mass. If the 1 kilogram mass is at rest, what is the tension in the string? For that, just draw a force diagram for the mass right here. You're just going to have the force of gravity down, mg, and the tension up. Those are going to be the same because it's at rest. So just summing your forces on that mass is going to give you 0 is equal to T minus mg. So T equals mg, which is just going to be 1 times by 9.8. So T is equal to 9.8 newtons, 10 if you're using 10, obviously. Assume that the tabletop is frictionless. What speed must the hockey puck have if the 1 kilogram mass is at rest? Okay, so now we know that we have T is equal to 9.8 newtons towards the center of the circle on that guy. So when we sum our forces on the little mass, um, we're going to have little m v squared over r is equal to t, right? Because t is the only force causing acceleration in that case. So we need to solve for the velocity. So v is going to equal, multiply the r over, divide the m over, square root it. So that's just going to give you 9.8 times by r, 0.5 over m, right? But you want to use the mass of the thing that's going in a circle, so you're going to use the 1.17, not the 1 kilograms. And you are going to get 5.4 meters per second. 4 meters per second. All right. Last one here. You take a hot date to the fair for a romantic Ferris wheel ride. You are contemplating going in for the kiss when the carny operating the Ferris wheel decides to turn the speed up to extreme. Needless to say, the moment is ruined, so you decide to focus on some physics. Good plan. You notice that when you're at the top of the Ferris wheel, you feel lighter than usual, and when you're at the bottom, you feel heavier than usual. Explain why. So, um, since you are traveling in a circle, you need to a net force towards the center. When you are at the top, you are top. That means that Fn must be smaller than Fg, so you feel lighter than usual. So there you go. Something to that effect should be good. Basically, you just need to be talking about the fact that the normal force is smaller than gravity. Okay, this one. The Ferris wheel is advertised as being 40 meters tall, so you know the radius is 20 meters. You use your phone and figure out that it takes 15 seconds to go around once. How fast are you traveling? So this isn't actually a physics problem so much, right? So I mean, it kind of is, right? But we know that velocity is the distance you go divided by the time. Since you're traveling in a circle, the distance that you go is the circumference of the circle by the time. So that's just going to be 2 times by pi times by 20 meters divided by 15 seconds. And you're going to get that your velocity is 8.38 meters per second. So there we go. Next one, you have a mass of 55 kilogram. What is your apparent weight? Apparent weight is the normal force at the top. So, let's see here. We just sum our forces for the top. At the top, right? You're gonna have small normal force and larger force of gravity. And so we of course have mv squared over r. And then towards the center is positive, so that's going to give us force of gravity minus normal force. So looking for the normal force, we're going to add the normal force to the other side and subtract the mv squared over there. So your normal force is equal to Fg minus minus mv squared over r. So that's going to give you 55 times 9.8 minus 55 times velocity. I'm going to need a little bit more room here, sorry. I'm going to have to erase that. We know we're going 8.3 squared divided by 20 meters radius. And that is going to give you a normal force. Let's just do this. Normal force is equal to 345.9. So what is your apparent weight at the bottom of the Ferris wheel? So when you're at the bottom of the Ferris wheel, you're going to have basically the same force of gravity that you had, and then a larger normal force. So in that case, sum of the forces is equal to mv squared over r. 2, opposite in this case, normal force, because it's positive towards the center of the circle, minus Fg. And that's going to give you, so then we're looking for the normal force again. So normal force is going to equal, add the force of gravity to the other side. That's going to give you mv squared over r is equal to, nope, not equal to, plus mg. So 55 times by your velocity, which is 8.38 over r, which is 20, plus 55 times by 9.8. And for that, you are going to get a normal force that is equal to 732.1. Okay, lastly, let's do part E, where it says find the critical speed, which is the speed when the normal force is 0 and you feel weightless. So let's imagine we're at the very top here. Okay, so which this is our, right, that's our force diagram here, number for part B, for something that is going that is at the top, right? So if you are just stopped, then your force diagram would have normal force and gravity equal, right? So then the faster you go, right, the normal force, so the faster you go, right, the bigger the mv squared over r part gets. And so therefore, the smaller your normal force is, right? If you look over at the equation that we wrote, here, this term, this mv squared over r term, was going to get bigger and bigger and bigger. And so at some point, and therefore, so then, sorry, then the normal force will get smaller and smaller and smaller. And at some point, right, like the normal force will basically be 0. So you would have just the force of gravity. So the critical velocity is the point where the normal force is 0, and the only force acting on you is the force of gravity, right? If you were to go slightly slower, then you would have a normal force. And if you were going to go slightly faster, then the critical velocity, you would kind of like fly off and not like stay in your seat. So that's what the critical velocity is. Basically, if you were to go, again, if you were to go slower than the critical velocity, then you would have to have a normal force. And if you were to go faster than the critical velocity, you would fly off. Right, this being relative to a Ferris wheel. It becomes slightly different if it's like a loop-de-loop, like if it was like a track and you had a loop-de-loop. It's a little bit different. Same thing is true. Critical velocity is always when your normal forces can be zero, and the only force acting on you is the force of gravity. Like that is always true, but the slower or faster thing is a little bit different if you have a loop. So, um, anyway, so basically what you're going to do is when you sum your forces, um, right, you have mv squared over r is equal to mg because that's the only force that's acting on you. So then we could solve it. You can multiply the r over, divide the m, v squared equals mgr over m square root. Oh, I guess. The m's, of course, would then cancel. And so you're just going to end up with v is equal to the square root of g times by r, which would just be 9.8, times by the radius, which is 20. So 9.8 times by 20 square root is 14 meters per second. And there you go. That's how to find the critical velocity. Thanks for watching, and I hope this went well.